So last time we had just started doing probability. And today we are going to continue with talking about distributions. And then we're going to end the week with a wonderful application, something called the probabilistic method. So I will leave that for the end, but I'm excited to talk about it because it is extremely cool. But let's start with talking about distributions. And distributions are essentially a little bit of an upgrade to our formalism for probability. So we'll keep adding new tools as we go along. Here is our most recent new tool. So before, we defined the probability of an event, E, which is a subset of some sample space S, to be the cardinality of E, divided by the cardinality of S. So essentially saying that each outcome in S is equally likely. So for added flexibility, we now are going to allow ourselves to assign different probabilities to different outcomes in our sample space. So we will assign a probability, which we write P of S, to each element of our sample space. We require that it must satisfy a couple of rules in order to behave like a good probability. So they're both quite simple, but let's write them down. So the first one is that each probability must be between 0 and 1. Fair enough. You cannot have less than 0 probability of doing something, nor can you have more than a 100% probability of doing something. And secondly, the sum over all elements of our sample space of the probability of S should equal 1. So this essentially is saying that the probability that something happens among all of the possible outcomes in our sample space, the probability that any one of them happens is 1. Which again, this is just saying that if we perform an experiment, we will get an outcome, and the probabilities will all add to 1. So we have a name for these things. This is what we are calling a distribution. So the set S which is, again, we're going to call our sample space, together now with probabilities for each element, is called a probability distribution. Which you can think of as, where does this word come from? We're essentially saying that the probability, we are allowed now to distribute it in various ways among the elements of our set. So you may be a little bit disturbed that we defined probability like this last time, and then we proved a bunch of things about it. Now we're making a new definition of probability. Why are we doing that? What happens to all the stuff we said last time? Well, the point is that this is an extended version but it fits sort of on top of the framework that we were using before. So everything we said before will still hold true. We just need to replace our definition of probability. So if we have a subset of the sample space in our probability distribution, we define the probability of this event to be the sum over the elements in the subset of P of S. So let me just write this statement again. Everything we proved or defined about P of E or P of E given F, etc., works the same with this new definition. So for example, conditional probability is defined exactly the same way, and independence is defined exactly the same way. Everything like this still works. So let's see an example of a probability distribution. In fact, let's give a basic example that links us up even better to what we were talking about last time. So let S be a set of n elements. The uniform distribution on S is defined by the probability of each element is just 1 over n. So essentially, this is just saying that, like we were saying before, any outcome is equally likely. And essentially, to say that every outcome is equally likely, that determines what the probabilities have to be, because we know they have to add to 1, so they need to just be 1 over the size of the set. So let's say this sort of again, but more explicitly. This is essentially what we were doing before. Because in this case, if E is some event which we write in terms of elements A1 through AN, then the probability of E is, in our new definition, our definition up here, it is the sum over elements in E, which is to say, let me say I equals 1. So I used n for the size of S, so let me not do that. Let me call this k. So it's sum from 1 to k of the probability of AI. So this is just plugging in our definition here and writing the sum in terms of this having written E as elements A1 through k. And now, well, what is this probability? Since we're using a uniform distribution, we have it here, it's just 1 over n. So it's the sum I equals 1 to k of 1 over n. That looks like a k. And this is just k over n, because we have k terms, which are all 1 over n. And that, of course, is, k is the cardinality of E, and n is the cardinality of S. So we recover our old definition of probability. So we can think of distributions as essentially being this kind of generalization of how we were talking about probability before. Before, we were restricting ourselves to working with uniform distributions, and now we are allowing ourselves to define new, more complicated distributions.